And a random variable, and this is what Wikipedia tells me, a random variable is a mathematical formalization of a quantity or object that depends on random events. To me, that definition means like nothing, right? It's just empty words. But here are some examples of random variables. If I were to use a random number generator, like on an Excel spreadsheet to just give me a random integer, I could select a student at MNU according to their student ID number. Everybody's got that like 5-digit student ID. And then what if I tracked down that student wherever they lived and measured their height? That would be a random variable. A random variable is one where before taking a measurement, you don't know what it's going to be. We could make statements about the relative probabilities of this variable, like what kind of outcomes would we expect from the variable, but we don't know precisely what the measurement is going to be until we measure it. So if we're talking about measuring a random student's height, I could say things like, the height's probably going to be between 5 foot and 6 foot, probably, but it's less probable that it's going to be between like 2 feet and 3 feet, right? That's less likely. I can make statements about probabilities, but I don't know exactly precisely what that number is going to be until I actually measure it. And so the same thing, there's some more examples, but like MNU survives on donations. So every year they make a report about the total donations that MNU receives. We don't know what that number is going to be. Until they actually publish that report and we read the report, we don't know what that number is. But we can still speculate and make budgets and make projections for like how much are we going to receive in donations during 2026. We don't know, but probability it'll be between like 1 million and 20 million. So less likely that'll be less than 1 million and less likely that'll be more than 20. But we can make statements about probabilities. We just don't know the exact value. Okay, that's a random variable. Today is all about vocabulary words, so I'm going to present a lot of definitions to you. It might get a little bit tedious, but 2 more definitions. A population is a group about which we're trying to make an inference. A sample is just a subset of the population where we take measurements. If I wanted to make an inference about, let's say, the height of MNU students, it would be really difficult for me to track down all 1,000 MNU students and measure their heights. But sitting in front of me is a pretty good sample. You guys are a subset of the population. And if I go ahead and measure each of your heights, which would be substantially easier, I would still get a good idea for the distribution of height among MNU students. And so a sample is just a subset of the population. And if we take measurements of a sample, it helps me make inference about the population. Exercise 1 says, a public health specialist wants to determine the distribution of body weight for adult males in the US. She enlists a group of 10,000 men to submit their body weight. She reports that the average body weight of a man in the United States is 198 pounds. In this example, what's the population, Maribel? It is. Okay. What is the sample? Anybody?
10,000.
Yeah, just the 10,000, right? It's the subset that we actually measured. Yep. All right, one more. The FDA is trying to determine whether 40 milligrams daily omeprazole is safe for adult females suffering from heartburn. They enlist a group of 50,000 women suffering from heartburn. 25,000 women are given the 40 milligrams daily omeprazole. The other 25,000 are given a placebo capsule that looks identical. What's the population? Maddie.
50,000 women?
No. Cody.
Adult females suffering from heartburn.
Yes. Exactly. We want to know whether it's safe for women in general, not just the 50,000. What's the sample, Maddie?
50,000 women.
Yeah. The 50,000 is actually the subset of the population that we're taking measurements on. In this case, the sample is split between an experimental group and a a control group, but yeah. Okay, a parameter is a characteristic of a population or a random process. A statistic is an estimate of a parameter that we can calculate. Most of the time in real life, we can never ever know the true value of a parameter. So the reason we care about statistics is because statistics, that is something we can calculate, and it allows us to estimate the parameter. So if you're a biologist and you want to learn about red kangaroos, you might find 70, that's a pretty good number, find 70 red kangaroos in the wild, sedate them, and then weigh them. What do you think in this situation the parameter is? What are we trying to learn about? Yeah. Specifically, if I'm like knocking these kangaroos out and weighing them, I'm trying to learn about the typical average weight of the population of red kangaroos. I'm doing that by taking a sample of them and then weighing them and then probably calculating an average, right? But the average from the sample that I calculate is not the same as the average for the whole population, right? The average for the whole population, that's a parameter. That's something we're never going to know. We're never going to capture every single red kangaroo and weigh them. But we can find a subset. And so the subset gives us a statistic. The average for my sample weights is a statistic that estimates the population average, which is our parameter. My third grade science class performed an experiment to learn about bread mold. We placed 10 slices of bread, slightly damp, in closed plastic bags and kept them like in a drawer in a dark place. If you observe the bread every day and you record the number of days that passed before each one showed visible signs of mold, what's the parameter and what is the statistic?
Would the parameter be like how quickly mold forms, like on average, while the statistic is how, it's like the average of how quickly the mold formed on the 10 slices of bread?
Yeah, exactly. Perfect. You guys got it. So the parameter is, what are we trying to make an inference about? We're trying to say, how long does it take mold to grow on damp bread, right? And that's a random process. It's not always going to be 2 days. Sometimes it's going to be 3 days, and sometimes it's going to be 1 day, right? So we don't exactly know what the sort of distribution mean is. We don't know what this parameter is, like the overall random process, what it's going to be. But what we could do is we could do this for 10 different slices, and we could calculate a statistic, like the mean time to show visible mold. And then our statistic is an estimate of the parameter. Okay, new words. A qualitative variable is one that places individuals into categories. So sometimes a qualitative variable is also called a categorical variable. Those are synonyms. And by contrast, a quantitative variable is one that assigns a number value to a characteristic or a measurement. So an example, exercise 3. A biologist goes to study finches on an island in the Galapagos. She records the color of the first 100 finches she finds. Is this a qualitative or quantitative random variable? Yes. Color is going to be qualitative because I can categorize the finches into red finch, blue finch, green finch, whatever. Qualitative places into categories. Okay. Back to the Galapagos. She records the beak length. Is that random variable qualitative or quantitative?
Quantitative?
Yeah. Because if I'm taking a measurement of the length of something, that's a number, that's quantitative random variable. A discrete variable, so again, 2 more vocabulary words for you. Discrete means it can have only a countable number of possible values. A continuous random variable is, by contrast, could have a continuous range of possible values. And I think maybe these vocabulary words, more than anything, really trip up students from this section on a test. So let's see, an exercise 4. A biologist goes to study finches. This time she records the number of eggs in each of the first 30 nests. Keely, is this going to be discrete or continuous?
I don't know. I'm confused on this one. I'm just gonna choose like discrete.
You're right. Very good. This is a discrete random variable because this random variable, the number of eggs we find, can only have a countable number of possible values. I either have 0 eggs, or maybe I find 1 egg, or maybe I find 3 eggs, or 7 eggs, but there's only a countable number of possible outcomes. I'm not going to find 3.14159 eggs, right? So it is discrete and not continuous.
Would continuous only refer to like decimal type numbers?
Yep.
Okay. I thought it was like, oh, and you'll have like 1,000 plus eggs, or like an infinite amount of eggs. But it's like, oh.
Even if there was 1,000 eggs, it would still be discrete,
Still be countable.
right?
Okay.
This time, if we record the beak length of the first 100 finches, is this random variable discrete or continuous? Continuous. Because if I measure the length of the beak, it could be 7 millimeters, or it could be 8 millimeters, or it really could be 7.614 millimeters, right? There's a continuous spectrum or a continuous range of values that a length could take on. Yeah.
So it's more about like whether or not the value is like a unit. So like, okay.
Yep.
So if it had any sort of decimal attached to it, it would be considered continuous. Even if it's like a small decimal, like 1.1.
Man, so this is it's a really good question, because the answer is like pretty nuanced and pretty subtle to this, because
Well, could it be the range? So it could be from 1.1 to like 100.1.
yeah, so really the word continuous means that my random variable could be any real number, and like length could take on any real number value. Discrete doesn't necessarily mean integer. Most of the time, like 99% of the time, discrete means integer, like we're counting the number of eggs or we're counting the number of people. But discrete doesn't have to mean integer. Discrete could it could be like this. If you had a roulette wheel, right, and you spin it and the little ball is flying around the roulette table, and then eventually the ball settles down here and it stops. And I don't know if you've seen a bunch of roulette tables, but like the ball will stop in a specific, like one of several spots. It can't be continuous around the table, but there's actually like a specific number of spots it could stop in. And so then if you say, well, let me take a random variable like this, and we'll measure the angle where the ball stops, it's not going to be a whole number. But since there's only a countable number of possibilities for this angle, this would still be considered a discrete random variable. So even though it's not an integer, there's still only a countable number of possibilities, and so it's still discrete. Now, you probably don't need to worry about it that much, because almost every time a discrete random variable is going to be a whole number, like a positive integer. but it's not necessarily the case. You can still have a countable number of outcomes if it's not an integer variable. Okay, so we're talking about beak length. Lengths are continuous because you could have any real number as your length. All right, more vocabulary. There are 4 levels of measurement that most stats textbooks discuss. The 4 levels of measurement are nominal, ordinal, interval, and ratio. Nominal means you are just categorizing. And when you make this categorization, there is no difference in value between the categories. Like, you would not have a natural way of ordering the categories. I'll give you examples of each one. But like, an ordinal level of measurement would involve categorizing, like I'm placing individuals into categories, but there would be a natural order to those categories. If you were just going to randomly grab people off the street in downtown Olathe and ask them, like, what was your highest level of educational attainment? People would tell you, like, some high school graduate, some college graduate, postgraduate degree, right? People would tell you which category they belong to. And of those 5 categories I just mentioned, there's kind of a natural order that you would place them in, right? Like, people with a high school diploma would, be less educational attainment than someone who has a college diploma. So there's a natural order to the categories, but nominal is just categorizing, where there doesn't really make a lot of sense to place them in order. It's like if I were to grab people off the street in downtown Olathe and say, what's your favorite fast food joint? And people tell me McDonald's, Burger King, Wendy's, Chipotle. Unless I specify some way to put those categories in order, there's nothing that jumps out. There's not like a natural way to put favorite restaurant in order. So that would just be a nominal level of measurement. In an interval level of measurement, the differences between values have meaning, and then in a ratio level of measurement, we're assigning values and the ratios between values have meaning. And that's probably the trickiest thing of all to understand. We'll get to that here in a sec. I'll get some examples for you. If we find 10,000 adults and we ask them what is their primary means of physical activity, what's that level of measurement? Nominal, ordinal, interval, or ratio?
Nominal?
Nominal, right? Because as far as I'm concerned, jogging, swimming, playing a sport, it doesn't really matter. Those are just categories, right? There's not a natural order to things. If you were to survey adults and say, how satisfied are you with access to healthcare in your area? What's the level of measurement? Ordinal, perfect. Because I am placing the respondents into categories. They fall into one of these 5 categories depending on how they answer my survey. But there is a natural order to the categories, from best to worst. If I step outside and look at my outdoor thermometer, what's the level of measurement for this random variable? This is interval. It's not ratio. It is an interval level of measurement. And let's go back to the definition here. At an interval level of measurement, the differences between values have meaning. So the difference between 30 degrees Fahrenheit and 40 degrees Fahrenheit feels about the same as the difference between 50 degrees Fahrenheit and 60 degrees Fahrenheit, right? We're both talking about a situation where we increase 10 degrees Fahrenheit and it seems like it's the same increase in temperature, right? It's noticeable, but not the end of the world. But this is not a ratio level of measurement, because if the temperature outside was 10 degrees Fahrenheit today, and tomorrow we woke up and the temperature was 20 degrees Fahrenheit, I would not tell you that it's twice as hot. That would be kind of silly, right? If, you know, I don't know how to say it anyways. The difference between like 1 degree and 2 degrees Fahrenheit is barely noticeable. So we wouldn't say, oh, it's twice as hot today. And moreover, 0 doesn't really mean 0 on the Fahrenheit scale, right? There isn't 0 temperature whenever you have 0 degrees Fahrenheit. So it's not a ratio level of measurement. It's only interval. That's the idea. Lastly, if you were to ask people how many minutes per week they spend exercising, what's the level of measurement? Ratio. Because 0 minutes per week of exercise really does mean they are not exercising. 0 means 0. And if you exercise 10 minutes per week and you exercise 20 minutes per week, everyone would agree you exercised twice as much as you did. So ratios make sense at a ratio level of measurement. So nominal, ordinal, interval ratio. Any questions so far? With all these new vocab words? Okay. John?
So like the difference between nominal and ratio, so just like numbers involved pretty much? Is that the difference? Or?
Between nominal and ratio?
Yeah.
Nominal is just categorizing, and ratio is like you take measurements and there's numbers involved, and yeah. Okay. The sample mean is probably what we're used to calling an average. You add up the measurements and you divide by the number of measurements. This might look a little bit goofy to you, so I'll try to explain the symbols for sample mean. This is a capital Greek sigma. And it means add them up. This overbar is the notation for sample mean. So if I draw a little x with a bar over it, I'm saying take the sample mean, take the average when you see the bar. So this formula is saying sum up all of the measurements, all of these x values. When there's a little subscript k, we call this an index. And it's telling you which measurement we're referring to. But in this case, we're just adding up all of the measurements. And then we divide by n, where n is the number of measurements. So you add up all the measurements and you divide by the number of measurements. If the index thing is throwing you for a loop, I'll give you a little example. Like I might say that x is a list of measurements for 9, 16, 25. I would say that x1 is 4, x2 is 9, x3 is 16, and x4 is 25. So the little subscript is telling me which measurement in my list of measurements I'm referring to. The capital Greek letter sigma says add up all of the measurements. The sample median is the middle value. If you order your sample measurements from least to greatest and you pick the middle one, that's the median. The sample mode is the measurement that occurs most frequently. If I've got a continuous random variable, there's not going to be a sample mode. Because if you're dealing with real number measurements, you're never going to get exactly the same measurement twice. But if I've got a discrete random variable, well, then we could have a sample mode because you could get the same outcome twice.
What if there's two middle, like say the ordered sample has like 6 numbers in it, but then the 2 middle numbers are different from each other? Would you take the average of those 2 numbers?
Yep, you take the midpoint. Yep, good question. So if I asked you, what is the sample median of this set in green? The median is halfway between 9 and 16. So it's 12.5. Okay, so if you've got an odd number of measurements, it's the middle one. If you've got an even number of measurements, it's the average of the middle two. Good question. So I could ask you a question like this in your homework where it says like exercise 6, find the sample mean, sample median, and sample mode of the following data set. The first thing I would do is I would put it in order. The median is easy, right? It's the middle one, so the median is 15. 18 appears twice, so that would be my mode. And then the mean, you would have to add up these numbers and divide by 5, right? So after I add them up, I get like 25 plus 30 is 55. 55 plus 18 is 73. 73 divided by 5. What is that? I don't know. You get the idea. I'm sure you've all taken an average before. All right. When is the sample mode meaningful? When is it not meaningful? And the hint here is, are we talking about discrete or continuous? If I had a discrete random variable, is it meaningful to ask about the sample mode, the most frequent outcome? Yes. If I have a continuous random variable, would it make sense to ask about the most frequent outcome? No. It doesn't make sense for a continuous random variable for this reason. If I'm going out and I'm capturing a bunch of finches in the Galapagos and I'm measuring the length of their beaks, are any two birds going to have exactly the same beak length? No. Maybe they're close to the same, but since they could have any real number beak length, they're always going to be off by a little bit, off by a micron or a tenth of a micron. So it doesn't really make sense to ask about a sample mode when I have a continuous random variable. It only makes sense for discrete cases. When is the sample median meaningful? When is it not meaningful? So let's think about the levels of measurement. The levels of measurement are nominal, ordinal, interval, and ratio. The median is the middle outcome. So if I have a ratio level of measurement, like the number of minutes you spend exercising per week, would it make sense to ask about the middle outcome from a sample? Yeah, I could order everyone's minutes of exercise this week and find the middle outcome, so that makes sense. What if I have an interval level of measurement, like taking the temperature in degrees Fahrenheit outside? Would it make sense to ask about the median, the middle measurement? Yeah, you could find a median temperature from a bunch of temperature measurements. Ordinal. So let's think about ordinal. What was our example for ordinal? Like whether or not people are very satisfied, satisfied, neutral, unsatisfied, very unsatisfied. If I have an ordinal level of measurement, would it make sense to find the middle response from a group of responses? Yeah, you can find a sample median in an ordinal level of measurement. What about if it's a nominal level of measurement? Like I ask everybody what their favorite sport is. No, there is no median response for a nominal level of measurement.
Why is there a meaningful sample median in ordinal?
It's a good question.
Because it's not a number, and it doesn't necessarily, like those are the, especially if it's like in the survey you were talking about with the satisfied, very satisfied, there's not necessarily, like you can look at that anyways. So why would it be meaningful? Does that make sense?
Yes, it is a really good question. Okay, so this is my survey. I can categorize people into one of these 5 groups. And let's say that it looks like this. Let's say 34 people said they're very satisfied. 21 people said they're satisfied. 2 people said they're neutral. 3 people said they're unsatisfied. And 9 people said they're very unsatisfied. The way I would go about finding my median is like this. I'm going to add up and find out how many people total answered my survey. In total, 69 people answered this survey. So that's an odd number. What would be the middle responder out of 69, right? I could do 69 divided by 2. It's going to be the 35th respondent, because there'll be 34 responses below and 34 responses above. So the 35th response is the median. And based on these numbers, the 35th response would have to fall in the satisfied category, right? Whether you number from the bottom up or you number from the top down, the 35th response is going to fall into satisfied. If you say the first 34 went to very satisfied, then the 35th is in the satisfied category. So we would say the sample median is satisfied.
Okay, that makes more sense.
Okay. When is the sample mean meaningful? So again, our levels of measurement are nominal, ordinal, interval, and ratio. If I have a ratio level of measurement, like minutes of exercise, can I take a sample mean? Yes, I can take an average. If I've got an interval level of measurement, like temperature, can I take an average temperature? Yes, that makes sense. If I have an ordinal level of measurement, like satisfied, very satisfied, neutral, unsatisfied, could I take a sample mean? Could I average those? Really? The sample mean formula says I should add up all of the measurements and then divide by the number of measurements. But what is satisfied plus very satisfied? It doesn't really make sense to add up the measurements, right? I can't add neutral plus unsatisfied equals what, right? It doesn't make sense. So we can't average ordinal level of measurement. Okay, this is a little bit tricky too, but take a stab at it. If I take a measurement of a continuous random variable, the act of measuring itself is a random variable. For example, there was a time when I was volunteering at the annual Lions Club breakfast in Lubbock, Texas. And it was a huge event that drew like 12,000 people to come eat pancakes for charity, right? They'd pay like $1 and get a dozen pancakes, and somehow they would still make money for charities. My job was to make the coffee, and they made these coffees in these enormous drums. Like, they were so big you couldn't wrap your arms around them. They like held like more than 50 gallons. But when I made a batch of coffee, which was just throwing in hot water and instant coffee mix, right, and stirring it around, I was supposed to let it cool so that the temperature was exactly 135 degrees. Because if it was too hot and it burned someone's mouth, then we get sued, and nobody wants to be sued, right? So if it was hot, I would throw in ice cubes until it cooled down. So if I were to look at this batch of coffee and say, I'm going to take the measurement by putting a bulb thermometer in, right? Like one of those mercury-filled thermometers. Take the temperature. I'm going to get some temperature measurement. And then I also go back and I've got one of those thermocouples, like one of the ones that you can poke into your turkey on Thanksgiving and figure out what the internal temp is, because it's got two metals of dissimilar alloy and they touch and they create a current. If I put a thermocouple in my coffee, I could get a measurement. And then if I get one of those cool laser temperature guns and I like just laser gun the coffee to get the temperature, I'm going to get a different refractive measurement of the temperature. Am I going to get exactly the same 3 temperature readings? No, why not?
Because they're reading the temperature different ways, so they're going to come out to slightly different.
Yeah, I mean, even though there's just one bulk coffee temperature, that just always happens, doesn't it? Like, I don't know if you guys have ever done this, but like, I step on my scale at home to weigh myself, and then I go to the doctor and I get weighed by the doctor on their scale. I get a different measurement. I'm the same person. I didn't change clothes. Why do I weigh different? It's just different measuring devices. So every measuring device is just going to be a little bit different. That's just how it is in the real world. So there's a little bit of randomness in the error of every measuring device. So that no measuring device will ever give you exactly, accurately the value you're trying to measure, if it happens to be a continuous variable that you're trying to measure. They're all going to have a little bit of error. And so you won't ever get the same measurement more than once. If we cannot determine the direction or the magnitude or the source of the measurement error, we call this indeterminate error. Indeterminate means we cannot determine the error. So like, I don't know why my personal scale is different from the doctor's scale. I don't know which one is actually reading the correct weight and which one is off. So I don't really know if the error is a positive error or a negative error. I don't know. So that would be indeterminate because I don't know. If I did happen to know the direction or magnitude or source of the error, I would call that determinate because we've determined something about the error, right? The more you know, the more determinate it is. So you can correct for determinate error if you know something about it. Maybe you know the direction. Is it positive or negative? Is it big or is it small? You could try to correct for that. But if you don't know anything about it, you cannot correct indeterminate error. And like we said, every measurement of a continuous variable always contains some indeterminate error. Bob wants to know the cold tire pressure of his front left tire. But he just drove his car from Tulsa, Oklahoma to Olathe, Kansas. So he can't measure the cold tire pressure. His tires are hot. If he measures the warm tire pressure, is this determinate error or indeterminate error? It's determinate. Because you know that the warm tire pressure is going to be higher or lower? Higher. Hot tires means a higher pressure. He's going to measure a hotter, higher pressure tire. So we at least know the direction, right? We at least know that the measurement's larger than it should be. And if he's taking a Gen Chem class, he can pull out his ideal gas law formula and plug in the values, and he can figure out by how much his measurement is off. But this is determinate, because we know something about it. Okay. Alice measures the weight of her baby with two different scales. The scales don't agree exactly, so she knows that both measurements can't be exactly accurate. Is this determinate or indeterminate? Indeterminate, because we really don't know where the error is coming from.
So even though you're aware of an error, it doesn't make it determinate.
Correct.
Okay.
There's always some error, but if you don't know how big it is, what direction it is, then it's indeterminate. Okay. Raise your hand if you've seen scientific notation before. Good. Yeah, I learned about scientific notation in like 10th grade chemistry, which is, I guess it's good. Didn't actually learn about this in a math class. But regardless of where you've seen it, it's probably the same. This is scientific notation. This number is called the mantissa. That's where the little lowercase m's are. You're going to see one digit, then a decimal, and then maybe several other digits after the decimal. And all of these are the mantissa. The little e is called the exponent. Where you got times 10 to the power e. And the exponent is always an integer. So it's going to be -3, -2, -1, 0, 1, 2, 3, 4, 5, etc. This says represent each of the following numbers in scientific notation. So I can show you a few of these, how it's supposed to go. If I were looking at this, I would call this 3.14159 times 10 to the power what? Five. Because when I move the decimal from after the 9 to after the 3, I go 1, 2, 3, 4, 5. 5 places over. And so that means I have to multiply by 10 to the 5th power to get the decimal back. And so that's how it works. We want this mantissa to be between 1 and 10, right? So like the number 3 only has one digit to the left of the decimal, and that is perfect scientific notation. What about 0.00245? I would want to write 2.45 times 10 to the power what?
It'd be -2. 43. Oops, I miscounted.
Yeah, okay, good. 3. It's -3, because this time the decimal is moving to the right, and it's moving 3 places to the right, so we call it -3. 2.45 times 10 to the -3. Next one. I'm going to have to put in some commas in here to 48,300,000. 48,300,000 is 4.83 times 10 to the power what? 7. Because we're moving the decimal 7 places to the left. 0.00007. That's 7 times 10 to the power -5. But that's okay. I know it's like small and it's far away, so it's hard to count zeros. Tough to count zeros. Okay, but everyone gets the feel for this? Any questions about how to do this? Okay. Stop me, raise your hand if you have questions. So we go the other direction and say, now I've got numbers in scientific notation. How do I put them in ordinary decimal form? If I see 10 to the third power, that means I need to move the decimal 1, 2, 3 places to the right to get 2,718.2818. If I've got 10 to the -4 power, what is this number going to be?
Like 0.000783024.
Perfect. Yep. Because if I wanted to recreate this in scientific notation, I go 1, 2, 3, 4. So even though this is a -10 to the -4 power, there's only going to be 3 leading zeros after the decimal. It's because the decimal goes after the 7. Okay, 9.372 times 10 to the 7th. This is going to be 9,372, and how many zeros out here? 4. Because I've got 10 to the 7th power, 3 gets eaten up by the 372, and then 4 more zeros make 7. And then what about this one?
0 point and number.
Yes. No. Sorry. It's not 0 point and then the number.
432,156.7.
There we go.
Yeah, got it right.
But that isn't exact.
So instead of 4,321,567, we get 432,156.7. Because all we're doing is we take the decimal and we move it 1 place to the left.
Yeah, but didn't you say that for it to be scientific notation, it's supposed to be between the numbers 1 and 10?
Oh yeah. So this is not in scientific notation, is it? To start off with. But I guess the exercise just says represent each of the following numbers in ordinary decimal form. But I guess to be consistent, I should have put a little decimal there. If I did put a little decimal there, then the first answer was correct. If this is the case, where a little decimal is there, then it would be 0.4321567. Okay. Very good. I feel like you guys get it. Significant figures. Have you guys heard about significant figures before? Yeah? Same group? Everybody who learned scientific notation learned significant figures at the same time? Okay. We'll go over it again really quick. The number of significant figures is the number of digits shown, but not including any leading zeros and not including any trailing zeros. And there's all sorts of exceptions to this rule. So we're going to go over a bunch of examples too, just so it's super clear. If you want to reduce the number of significant figures, you round. Rounding means you go up if the next number is greater than or equal to 5. You round down if the next digit is less than or equal to 4. Exercise 15. Represent each of the following numbers in ordinary decimal form with the specified number of significant figures. So this is not scientific notation. We're just trying to get 3 sig figs on this number here. So how do I write it?
Would
would that just be 3, 1, 4? Those significant figures, or?
3, 1, 4 would be my significant figures. But I do have to keep the zeros. So before rounding, I've got 314,159. After rounding to 3 significant figures, we only report 314,000. We say that the 159 is insignificant based on the 3 sig figs. What if I want 2.7182818 with 4 significant figures? What is that going to be? 2.718?
But then you just wouldn't drop the zeros because they're after the decimal.
Right, we don't need zeros after that. Yeah, I needed these zeros.
Because otherwise it would change the whole number.
Yes. We need these for place value. But we don't need these zeros. All right, how do I write the number 1 with 5 significant figures?
1.000040.
Yes, that's it. So I don't need those zeros for place value. I don't need to write 0.0000 for place value. But if you were to see this in like a scientific article, that's communicating to the whole audience that reads the paper that we have a precise enough measurement to know that this is 1.0000 rounded to this decimal. And so the number of zeros you have trailing after the decimal is an indication that communicates something. It communicates how precise are we, how precise is our measurement. All right, 0.0783024 with 2 significant figures. What would that be? Seven and 8 are the significant figures. The 3 is less than 5, so it rounds down. I don't need any trailing zeros. I do need this leading 0 for place value. The significant figures are the 7 and the 8, but they keep the zeros for place value. All right, the next one is 43.00002157 with 4 significant figures. What's that going to be?
Would just be 43.00.
Perfect. So remember the 0.00, those are significant figures. It is communicating that we know this with precision. I can't stretch it out to get to the 2, otherwise I would have like 7 sig figs.
Is there like a cap on how many significant figures you can have?
You wouldn't want to have more significant figures than you have precision, right? If I was going to measure someone's height, right, I would have your height down to maybe like 1/10 of a centimeter. And so I'd say your height is 140.5 centimeters. I would not say your height is 140.5134682 centimeters because I just don't know that level of precision with our available measurement devices. So you only want to include the sig figs you're actually confident with. You don't want to include more than you have to. 5,000 with 2 sig figs.
Wouldn't that still be 5,000?
Yes. Because the first 50, these are my significant figures. But we need these for place value. So yeah, it is still 5000. I'll give you a moment to read this because it kind of drives the point home. So that kind of, I think, goes to Ray's question, right? Where Ray was like, how do you know how many sig figs to report? Well, you don't want to give more significant figures than you have confidence in. And the joke here is that after some horrible cataclysm that killed 500,000 people, right? Like maybe like a nuclear detonation or something like that, you wouldn't know 5 significant figures of accuracy in the casualty toll, right? And so that's the joke, I guess. A little bit gruesome. All right, represent each of the following numbers in scientific notation with a specified number of significant figures. Okay, so this time we're doing it in scientific notation. And 3 sig figs. So what would this look like in scientific notation with 3 significant figures? 10 to the 5th. Yep, so we got to move the decimal 5 places. And then I just keep 3.14. I don't keep the rest of it because of 3 sig figs. Let's do this one. 0.07833024 with 2 significant figures.
It'd be 0.078 times 10 to the power of negative 2. No, it wouldn't. No, it wouldn't. No. 7.8. Then it'd be 2 negative 2.
Yep. 7.8 times 10 to the negative 2. So the 3 rounds down. We got to move the decimal 2 places over. Okay. What is this with 4 sig figs?
43.00. No.
Remember, we're doing scientific notation.
4.3. Would it be to the power of 1? Yeah.
It is times 10 to the power 1.
Yeah. 2 more zeros.
Yeah. I need these zeros to be significant figures. So I've got 1, 2, 3, 4 significant figures. And then I move the decimal 1 place. All right. What if I want the number 5,000 with 2 significant figures written in scientific notation? What is it? Yeah. So this time I only need 2 sig figs. So there's 1, 2 significant figures. 10 to the 3rd tells me it's 5,000. All right. Got this question a lot last semester. If I get out my calculator and I type in 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9. Oh, that doesn't do it. Times 10 times 11 times 12 times 13. Oh, it's still not there. Times 14 times 15 times 16. Okay. Oh, it doesn't even have a little e. Let me try something else. This TI-30X2S calculator actually has a little tiny times 10 to the power. What I'm thinking of is this. I guess that's not a big enough number. There we go. What does this little e mean? Times 10 to the power. Yep. That's just scientific notation. 7.7777777 times 10 to the power 20. That's how you read the e. All right. This, I think, is something that maybe nobody has seen before. I know that maybe so much of today has already been a review of what you learned in 10th grade chemistry, but we've got an exception for significant figures But this is the special case, and it happens to matter later on in this class, later this semester. If you've got a fraction, and your fraction is necessarily between 0 and 1, okay? An example is like, what percentage of MNU students are younger than 50 years old? Okay, that's a fraction between 0 and 1. It can't be more than 1, can't be less than 0. And not only that, if I ask you what fraction of MNU students are less than 50 years old, that's probably a fraction that's really, really close to 1. Like, it might be like 99.99%, right? That's what I'm talking about here in exercise 17. Represent the following numbers using the specified number of significant figures. If I wanted 0.99999423513 with 3 significant figures, I'll show you how to do this the wrong way. I could say, well, round up, right, because of the 9. So 1. But that is misleading. I think that's misleading. If you've got a number that's not quite 1, because it's a fraction that's really close to 1, I don't like the idea of rounding it to 1, because 1 makes it sound like everybody's younger than 50. And maybe there's that one guy who's 55 years old taking classes at MNU. So this is misleading, in my opinion. So here's what we're going to do, and it's kind of tricky, but we are going to pretend that the 9s are like 0s. They're just there for place value. They're not actually significant figures. So pretending that the 9s are just there for place value, this would become 0.12345 1, 2, 3, 4, 5, 424. Sorry. I know I'm still using a red pen, but that's the correct way of doing it.
Would that not be 423?
But the next digit is a 5. So we got to round up. 5s round up. 5s round up, 4s round down. So it would be 424.
So if it was a 6, you'd still round up to 4.
Yes.
But if it was a 9, you wouldn't round up to 4.
If it was 4239,
Yeah.
then we would round up to 4. Yeah, that's how rounding works, you guys.
She's confused about the first 9s being placeholders, and that
Yeah.
if there was another one, it wouldn't be. That's what she's tripping about.
Yeah.
It's only the leading 9s, right?
So if there are leading 9s. Oh! If there are leading 9s, you treat them as 0s. That makes a lot more sense when you say it like that.
This 9 would round that up to a 4.
Yeah. Because those are the significant figures. I was looking at the first 3 9s as significant figures.
No, so these 3 are 3 significant figures. The 9s are just for place value.
That makes sense. So if 9s are leading, you always treat them as 0s.
Yeah, so this one 0.9995154, right? Because 5154, that's my 4 significant figures.
And that one you wouldn't round up because that's a 3 out of 4.
All right, I realize I've got 2 minutes left, so we'll wrap this up with 2 more comments. When you're doing a calculation in this class, keep 1 or 2 more sig figs while you're calculating. If you're doing a bunch of stuff in your calculator, let's say you know you want to report your answer with 4 significant figures, go ahead and keep 6 significant figures while you're doing your calculation. And then when you report your answer with 4 significant figures, you know that all 4 of them are going to be accurate. You're not going to suffer from any kind of round-off error. If you only keep 4 during your calculation, then you might suffer from a little bit of round-off error when you report your answer. The last thing is, if I don't specify how many significant figures you should keep, just keep 4, right? If you have a test question and the answer on your calculator is 12 digits, and I don't tell you how many to keep. Just give me 4.